So ANOVA can clearly tell you, do you have any difference or not, using as many factors as you want. But there is one problem. ANOVA doesn't tell you how big the difference is. So it tells you only one thing, that there is a difference. You have no idea which group is different and how big the difference. Okay. So what we need to do? Of course, we can use still a pairwise t-test with Bonferroni correction, but in this case, we have actually a better option, which is called a Tukeys test for multiple comparisons. Okay. Well, first of all, the Tukeys test, it has several names. It can be Tukeys test for multiple comparison, Tukeys honest significant difference test, or just the Tukeys test. Tukey, it's a name of statistician, so don't mix it with Turkey, as many students do. Okay. Well, the idea of Tukeys test is it calculates, it tries to estimate how big the difference of means is for every pair in your groups. And then it can do it separately for every factor you have. For example, if you have, like in the previous example, we have apples. So we have 3 different combinations for the trees, and then we have only one combination, rain versus sunny, for the weather. The Tukeys test is based on ANOVA results, so it doesn't calculate anything new. So it means that you don't have to provide the values. It will use all ANOVA results to calculate the pairwise difference. And sometimes because of this, it's called post hoc test, so it depends on the previous test. Okay. And you can find out that, in fact, Tukeys test is very close to t-test, but it has a certain correction for the multiple comparison. We will discuss which one. Okay. It works if the requirements are the same as ANOVA. The observations and groups are independent. The values within each group are normally distributed. And then groups have almost equal difference, almost equal variance. Okay, and you remember that if we have some minor violation of the last two, the methods will work anyway. Okay, let me show you how the comparison between t-test and Tukeys test. You remember in t-test, if we want to get a p-value, we need to calculate a t-value first. T-value tells you how far the average of your sample is from the your null hypothesis average, assuming average of the population in standard errors. Okay. In Tukeys test, we do the same, but we call it a Q-statistic, because you can assume that we will use another distribution. And then the only difference is that we have a 2 here. Okay, but otherwise it looks absolutely the same. If you want to calculate confidence interval, you need to get a t-value for a given significance. And you remember that the t-value depends on 2 things. It's significance level and the degrees of freedom. If you look at this formula, it looks pretty much the same. You still have this square root of 2 here, but instead of t-value, you use a q-value. It's another statistic, and it depends on 3 things. It depends on significance level, it depends on number of groups, and then it depends on degrees of freedom. In this case, it's n minus k, where k is number of groups. Okay, so we just use another distribution. If t distribution takes into account sample size, how small the sample is, the q distribution also takes into account how many groups you compare using the same sample. That's it. Okay, and then if t-value follows t distribution and depends only on degrees of freedom, then the q-value follows q distribution, depends on degrees of freedom and the number of groups. Okay, so that's the difference. We will not talk in details about q distribution. I'll just show you how to use a Tukeys test and then how to interpret the results. So you remember this example with animals, where we found out that there is a difference. The f value was very extreme. Let's see what Tukeys test gives us for this example. Okay, so this is just a screenshot of a Tukeys test in R. Let's see what it gives us. First of all, you can see that this is the results for diet. It's our grouping factor. And then these are all possible groups. So in this case, I'll just take all possible pairs. For example, it compares B with A, C with A, D with A, C with B, D with B, and D with C. The first column, it's called the difference. This is the difference you observe in your sample. For example, if you see this 5 here, it means that the average for B minus the average for A, 66 minus 61, which is 5. Okay. Then you have 7 here. It's the average for C minus the average for A, which is 7, right? So it's just the average you observe. Then the next 2 columns, it's a confidence interval. By default, it's 95%. You can change it. 95% confidence interval for this difference for the population. Okay, so if you take the first case, B minus A, you can see that we can expect with 95% confidence that the difference between diet B and diet A will be between 1.2 and 8.8 seconds, the coagulation time. We are talking about coagulation time, okay? So it means that diet B gives you a higher coagulation time than diet A. How big the difference? Well, at least by 1.2. We don't know. At least by 1.2 up to 8.8 with 95% confidence, okay? If you compare diet C and diet A, we can see that diet C gives a higher coagulation time than diet A. And then how big the difference is? We don't know, but at least by 3.17 up to 10.8 with 95% confidence. Okay. And then the column, it's a p-value for each pair. Okay. So how likely we get samples B and A like they are if there is no difference between the populations, corresponding populations. And then you can see it's 0.8%. It's pretty unlikely, okay? For C and A, it's even more unlikely. But for example, if you take DNA, and you can see that DNA, they have the same, right? So it's 61 and 61. You can't see any effect because the samples are not different, okay? Then you also have significant difference here and also quite small p-value, okay? So that's a very simple thing. So Tukey test just does all the pairwise comparisons. And which test to use, the Bonferroni correction and t-test or Tukey's test? It depends. Well, usually if you use a Nova, Tukey's test is the best. It's the easiest thing to do. But if you, for example, you do not compare means but use some other tests, or for example, you don't have to compare all possible pairs, but you are interested in only particular ones, then you can just use the Bonferroni correction. You can also represent the results of Tukey test graphically in R. I'll show you the code later. This is how it looks like. So you have, this is a difference of means. Okay, this is the observed differences on your sample. Okay, and then the bar is the confidence interval, 95% confidence interval, and this is the zero. You see the zero limit. So you remember that if confidence interval crosses zero, it means that there is no difference. If it's positive, like here, it means that the first group has the bigger difference than the second group, and then if it's negative like this, the first group has the smaller difference than the second group, and then you can see all pairwise, all pairs. So it's quite useful to show the differences visually, how big the differences are.